Hi, my name is Reagan Wakefield, and this is my Physics 2211 Motion of a Falling Slinky lab. The purpose of this lab is to observe and investigate the motion of a fallen slinky from rest. Our overarching question is, does the bottom of the slinky remain stationary? For this lab, we will compare two models. The first model is an experimental model using Tracker, and the second is a computational model using GlowScript. The first fundamental physics principle used in this lab is Newton's second law, which states that an object's acceleration depends on the force acting upon an object and the object's mass. The second principle is drag, which states that due to air particles, there is a drag force on objects that is in the opposite direction of the object's motion. Finally, gravity is a force that pulls objects towards their masses, in this case, towards Earth. For the experimental method, we will be dropping a slinky from a position of rest and investigating its motion through an online tool called Tracker. The system is the slinky, and the surroundings are everything else around the system, such as gravity and drag. We will use numerous important formulas for our computational model. The first formula we will use is Newton's second law, which states that net force is equal to the change in momentum over the change in time. From Newton's second law, we derive the position update formula and the velocity update formula. The position update formula states that final position equals initial position plus average velocity times the change in time. The velocity update formula states that final velocity equals initial velocity plus net force divided by mass times the change in time. In addition, the force due to gravity is equal to the mass of an object times the acceleration due to gravity, and it points in the negative y direction. As we will see later on in the presentation, the bottom of the slinky will remain stationary until the top of the slinky reaches it. I used this video and tracker to track the motion of the slinky by plotting its position as a function of time. I chose my axis so that right is positive x, up is positive y, and the origin is the bottom of the slinky. I also set the calibration length to be 1.75 meters. As you can see in the video, the bottom of the slinky remains motionless until the top of the slinky reaches it. Moving on to the computational model. Here are some excerpts of my code that indicate the initial conditions. I set the object's mass to be 0.25. I set the initial position to be 4.447 e to negative 3 in the x direction and 4.368 e to negative 4 in the y direction. I found these values from my tracker data. I also set the initial velocity to be 0 because the slinky begins at rest. I set delta t to be 0.016. I obtained this by dividing the total time of the video by the number of frames. I also set g, the acceleration due to gravity near the surface of the Earth, to be 9.8. Finally, I set the proportionality constant b equal to 0.5. I obtained this number through trial and error. Here are my two while loops. The first while loop is when t is less than 0.45. This is the time it takes for the top of the slinky to reach the bottom of the slinky. Within the first while loop, I set the weight to equal w and the tension force to equal ft. I added these forces together to get my Fnet. I then used the position and velocity update formulas to update the object's position and velocity. The second while loop is for when the bottom of the slinky is no longer stationary and falls to the ground as well. I calculated the net force within the second loop again. However, this time we must add drag to our Fnet because the slinky is falling to the ground. We then use our new Fnet and the position and velocity update formulas to update the slinky's position and velocity. Here's a position first time graph of the data from the experimental and computational models. As you can see, the data is similar at the beginning, but as t increases, the data begins to diverge. The data is similar at the beginning because the bottom of the slinky is at rest in both the computational and experimental models. As t increases, though, the computational model has a more linear trend in the negative y direction, while the experimental model is less linear in the negative y direction. This discrepancy is most likely due to human error using Tracker. Our follow-up question is, does the bottom of the slinky stay stationary and why? The bottom of the slinky does stay stationary until the top of the slinky reaches it. This is represented in both of our computational and experimental models. This is because the weight and tension forces act in equilibrium and cancel each other out. However, when the top of the slinky meets the bottom of the slinky, the drag force increases and the slinky begins to fall. Finally, some sources of error within this lab are human error due to Tracker. I had some issues finding the position of the falling slinky with Tracker, and this can account for some of the discrepancies in my results. In addition, I found the proportionality constant through trial and error, so there could be potential errors because of that as well. Thank you so much for watching.